first, if we look at the Fourier transform of the analog signal or system, we get this equation here. So there is this integral going from minus infinity to infinity. This is our analog signal or system, and then there is this exponential to the power of minus j omega t, and here the superscript denote the continuous version, and we have this omega, which is equal to 2 pi times frequency, and this omega is the angular frequency. So if we now compute the Fourier transform for the sampled signal, so we are multiplying our signal with the Dirac sequence of the train of Dirac impulses, we can make this replacement. So we substitute this s of t by the sampled version, so it's the s of t times this Dirac sequence. So we replace here, and we will obtain the sum, because only at the sampling time instance the integral is non-zero. We can see from this equation, and we get this sum, and now the superscript d is denoting the discrete version. So we have from here, we went from the continuous version to discrete version, we made the substitution here, and we go from an integral to this sum. And we can see that the frequency variable only appears as omega times n times capital T, and as we said before, T is the inverse of the sampling frequency. So we have this relation here, omega times capital T is equal to omega divided by the sampling frequency, which is defined as this capital omega, and this is what is called the normalized frequency. The normalized frequency is without a physical unit, since the hertz in the omega and in the sampling frequency cancel. And in the normalized frequency, 2 pi represents the sampling frequency, and pi is the so-called the Nyquist frequency. So this is the upper limit of our usable frequency range, and it's defined as half the sampling frequency. Observe that we use the capital omega to signify that this is the normalized frequency. The capitalized version is commonly used to distinguish it from the continuous non-normalized version if both are used. So otherwise, the small omega sometimes is used in the literature for the normalized frequency. If that's all we need, there's no danger of confusion. But we are going to use usually the capital omega for the normalized frequency. To convert the normalized frequency back to the non-normalized one, we simply multiply it with the sampling frequency. So the omega, small omega, is equal to the capital omega, so this is normalized, times the sampling frequency. And to indicate that now we are in the discrete domain, we will rename our signal to x of n. So this was the s of t, now becomes s of n times capital T, and this is our x of n. And then we see that it's the spectrum or the frequency response is given by this summation here. So this is the frequency response. So here we have the normalized frequency. There is the sum from minus infinity to infinity. This is our signal in the discrete domain, and we have this exponential to the power of minus j capital omega times n. And this equation here we call the discrete time Fourier transform. This is DTFT because we apply it to the discrete time signals x of n. This can be distinguished from the discrete Fourier transform because the above time signal has infinite length. So we are going from minus infinity to plus infinity. So as n is an integer here, so it's not a real value like t, we have a 2 pi periodicity for the frequent response. So this is a very first important property of discrete time signals, that they have 2 pi periodicity for x, capital X and capital omega.